Hey everybody, this is a pretty big video on rolling motion, which is the culmination of all of the stuff that we've been talking about in rotational motion up to this point, all in one beautiful topic. Now, rolling motion itself is something you see pretty commonly every day, and you'd be surprised at how nuanced the physics behind such a simple motion is. So to start out, I'm going to ease you into the idea of rolling motion and what that really entails. And to start out, we're going to look at first just an object that's rotating on its own. This is what we've been focusing on the whole unit. When an object is rotating like this, we talk about its tangential velocities as being relative to this point of rotation here, this axis. And when we're looking at those velocities, you can imagine that points on the top and bottom, respectively, are both moving at the same velocity, tangentially, but in opposite directions, because a point over here needs to be traveling to the right, whereas a point at the bottom over here needs to be traveling to the left. Now, when an object is translating, on the other hand, we look at it a little bit differently. If an object is translating, then every single point on that object needs to be traveling with the same velocity at the same direction every time. And what a rolling object does is both things at the same time. And if you think about what the velocity vectors look like here, and the fact that they're both translational, well, if we've got the top of the wheel here traveling already with some velocity just due to rotation alone, and then we have the top of the wheel also needing to just have a velocity due to translation itself, then we get a funky scenario where these velocities, due to both types of motion, have to add up to give us that simultaneous rolling motion. So we've got two velocities to the right at the top. We've only got one velocity to the right in the middle. And then we have two velocities of equal magnitude, but opposite direction at the bottom. If you think about what the total of this is going to look like, it's a little hard to digest. A rolling object, an object that's rolling without slipping, I should say, as the top of the wheel moving at twice the velocity that the overall object is moving with, which is this just singular velocity down here. That at the same time, the bottom of the wheel technically is not moving at all relative to the surface that the object's rolling on. And a good way to think about this is to think of a lower dimensional object, like a polygon or something, where, if we only have a couple of points where our object could be in contact with the surface, then the lower you go, the more it makes sense, or the easier it is to imagine how this point has to be stationary for this object to continue moving. Because otherwise, we might as well just slide it across the ground. The point of contact right here is experiencing static friction with the ground, and that is what's causing this object to roll and translate at the same time. A better way to visualize this is with some animations. So right here, this is an O-physics simulation that shows the rolling motion and the velocities attached to the different points relative to certain components. So we're going to start with the first diagram, the rotation one. And the velocity component due to rotation relative to the axle here is constant, like that. The thing that's changing, though, is the direction of this velocity. Notice that it's always tangent to the rim of the wheel, like you'd expect. Now, if we change this so that we're showing the velocity component due to the axle movement, so relative to the surface, we get a very different picture. Again, we get a velocity component that's constant in value, but the direction of it is always pointing to the right. 100% of the time, because again, this is all relative to the axle, the point of rotation that is translating across the ground. Okay, and finally, we're going to show the resultant velocity vector. So this is all relative to the surface. This is how those two previous diagrams are adding up with each other. And if you follow this one, you're going to notice a very big difference. Now we've got this very strange situation where if we're just looking at the object itself objectively without any weird relative stuff, then we get that picture of how the velocity is twice the amount at the top, and at the very bottom if we're just looking at that moment in time, see if I can get it closer, then if that point relative to the ground at that exact moment is stationary, and it only begins accelerating after it's served its purpose, after it's lost contact with the ground again. Another good way to think about it is to imagine a person that's just walking on the ground. Earlier on in physics, you often learn about static friction under the context of someone walking. And when you're walking on the ground, it's uncomfortable, but even though you're moving across the ground, your foot, which we could consider to be this point here, is stationary relative to the ground. Otherwise, it's very uncomfortable to walk. That would be like trying to walk on a slippery surface or on ice, where yes, you could be propelling yourself forward, but your foot itself is stationary relative to the ground. So keep these animations in mind while we're going through this, because it does help to visualize how this all is unfolding, how it's all going down. So to finish up here, when an object is rolling, based on this here, where we're combining rotational motion and translational motion together, an object that's rolling is going to have two things. First, it's going to have rotational kinetic energy. That's from the object just rotating. Even though it's still moving, it is rotating, so it does have that form of energy. Mass is rotating about a singular point. In addition to that, we've got translational kinetic energy. And this translational kinetic energy is just from the whole object itself moving along with some velocity on its own. And when you combine those two together, that's when you get rolling motion. Now, there are two different types of rolling motion. The first one is going to be rolling without slipping. Now, that's the more common version, but there are some unique situations in which an object could roll with slipping. And to give you an idea of what that looks like, again on O-Physics, I have the simulation here that shows the motion of an object that does both, that begins out by rolling with slipping and then transitions smoothly into rolling without slipping. Now, this basketball here has an initial translational velocity that it's going to start with, and friction isn't going to be able to keep up right off the bat. And when this happens, watch. So you notice that as it travels along, it still is sliding visually. I'll play it again. It's sliding initially, and while friction takes its time to start exerting a torque on this ball and accelerate it angularly, it slowly transitions into rolling without slipping. One thing that happens from this that you'll notice is that our initial velocity here was about 5 meters per second at the very start. By the end, the velocity of the ball itself has technically gone down, because if you imagine it's starting out with all translational kinetic energy at the start, at the very end, that kinetic energy has to be split between the two forms, translational energy and kinetic energy. In the process, because you have kinetic friction slowing this object down a little bit, there is also a little bit of energy that's drained out of the system in the form of thermal energy. You see this situation a lot in real life when you go bowling. When you throw a bowling ball, you're giving it only translational kinetic energy mostly. And by the time that it hits the surface, it slides a little bit while it picks up steam rotationally, and then it kind of barrels down the rest of the alley with that combination of both. Now, depending on the situation you have, there are different equations that you're allowed to use because of how different those two types of motion are. When an object is rolling without slipping, that's the ideal situation in which all of the tangential velocities are in agreement with each other. There's no mismatch between rotation and translation. If that's the case, you can use a lot of those conversion equations from tangential to angular. For instance, we can use the conversion from linear to angular velocity v equals r omega. We can also use the acceleration version of that, where the linear acceleration is equal to the radius times the angular acceleration of the object. What we cannot use here is friction, mostly. And that's because, well, the object isn't really sliding anymore. It's static friction, and static friction is changeable. It's never one constant value. So you never really know anything other than that the force of friction is less than the static coefficient times the normal force of the object. And this isn't really definitive enough to give us any helpful information when we don't know more about the system itself. So for that reason alone, I'm going to go ahead and mark that this is an equation that, we can talk about, but it isn't very helpful for the situation. So this is all we've really got. Now, on the other side of things, while the object is rolling while slipping, we can use the force due to friction formula, because in that situation, we have kinetic friction at play. And kinetic friction holds a constant value while it's active until the surfaces, which are, the tire and the surface it's rolling on, are still sliding relative to each other. Kinetic friction is at play, and we are allowed to use that. However, now there is a mismatch between the velocity that the wheel is spinning at and the velocity that the wheel is moving with. And for that reason alone, we are no longer allowed to use these equations over here. So if you want to note that these are just strictly not allowed while this is happening, we can write those out again, but that's a big no-no. We can't use those here. We can use friction though, and that does help us. So the last two things are when we could maybe combine these two together. And that's really if static friction is at a maximum. What I mean by this is that, static friction does build up to a maximum point before it breaks down into kinetic friction. If that's the case, then we know definitively what that value is, because in this case, the force of static friction is equal to the static coefficient times the normal force. Just know that it's not always the case. This is still technically an inequality. And finally, we're only going to consider situations where friction's removing mechanical energy from the system if the object is rolling and slipping. And this is again for the reason that static friction isn't usually removing any energy from the system actively. Kinetic friction definitely is, because it is a force that's constantly applying this negative work to the system. It's draining energy out by applying negative work. And with that, in two of the next videos, we're going to cover two examples that cover these ideas in more detail, and how you can apply all of the equations that we've been using through this unit to a couple of different situations. So I hope this video gives you a better understanding of how we roll, and I will catch you on the next two. Peace.